April 1940, Fort Monmouth, New Jersey, U.S. Army Signal Course Testing Facility. Captain Harold Peterson watches a soldier struggle with the SCR-194 backpack radio, a beast weighing 70 pounds with batteries, requiring 2 men to carry and operate effectively. The soldier staggers under the weight, trying to maintain radio contact while moving through a simulated combat exercise. Peterson has been tasked with an impossible mission: develop a portable radio that one soldier can carry and operate while fighting. A radio small enough for infantry squad-level communication, light enough that a radio man isn't just a pack mule, rugged enough to survive combat conditions. The problem isn't transmitter design or antenna technology. The problem is vacuum tubes. Standard radio tubes in 1939 are enormous by modern standards, roughly the size of a small drinking glass with 8 thick pins protruding from a Bakelite base. Each tube generates significant heat and draws substantial power. A basic radio receiver requires at least 5 tubes. Add a transmitter and you need 8 or more. Stack them together with batteries, controls, and housing, and you get equipment that weighs 40 to 70 pounds. Peterson knows what he needs: tubes 1/4 the size, 1/4 the power consumption, just as reliable. But no such thing exists. What he doesn't know is that 90 miles north in Camden, New Jersey, RCA engineers are racing to solve exactly this problem. They're developing a revolutionary tube design that will change military communications forever. A technology so important that by 1945, millions of these miniature tubes will be in service worldwide. This is the story of how American engineers miniaturized the vacuum tube just as war demanded portable radios. How the challenge of making tiny glass envelopes with integrated bases solved a critical military problem. And how a technology developed for consumer pocket radios in 1939 became essential to Allied victory by 1944. Let me explain why vacuum tubes in 1939 were so large, because understanding the constraints makes the solution more impressive. A vacuum tube contains several precisely positioned electrodes inside a glass envelope evacuated to high vacuum. The cathode emits electrons when heated. The control grid regulates electron flow. The plate collects electrons. In a pentode, 5-element tube, there are additional grids for screening and suppression. The traditional manufacturing method, inherited from light bulb production, used a pinch seal. The electrode assembly was inserted into the bottom of the glass envelope. The glass was heated to softening point and mechanically squeezed, pinched around the support wires, sealing them in place. This created a vacuum-tight seal. But the pinch seal had inherent limitations. The glass had to be thick enough to survive the pinching process without cracking. The electrode wires had to be sturdy enough to support the pinch without bending. The resulting structure was necessarily large and required a separate base, typically molded bakelite with metal pins inserted through it. Standard octal tubes, 8-pin base, introduced in 1935, were about 4.5 inches tall and 1.3 inches in diameter. They weighed approximately 35 to 40 grams each. Power consumption varied, but a typical tube drew 0.3 amperes at 6.3 volts for the heater alone, nearly 2 watts just for heating the cathode. For a table radio plugged into wall power, this was acceptable. For a portable radio carried by a soldier, it was catastrophic. Battery technology in 1939 was primitive by modern standards. The best available A battery, for tube heaters, was a lead-acid or heavy-duty dry cell. The B battery, for high-voltage plate supply, was large and expensive. A radio using 5 standard tubes would drain batteries in hours of operation. The U.S. Army Signal Corps had been requesting portable radio system mid-1930s. Multiple manufacturers attempted solutions. All failed, due to the tube problem. You could build a portable radio with standard tubes. The SCR-194 proved that. But it required so many batteries and was so heavy that portable became meaningless. What the military needed wasn't just a smaller radio. They needed fundamentally different vacuum tubes. The Radio Corporation of America in 1939 was the dominant force in American electronics. Founded in 1919, RCA held crucial patents, manufactured tubes by the millions, and operated NBC radio networks. David Sarnoff, RCA's visionary president, understood that the future of electronics lay in miniaturization. Sarnoff had been pushing for a personal portable radio, a receiver small enough to fit in a coat pocket or handbag. This wasn't just about convenience. Sarnoff recognized that whoever controlled portable radio technology would dominate both consumer and military markets. RCA's engineering team tackling miniature tube development included some of the best tube designers in America. They faced multiple interconnected challenges. Challenge 1. Eliminate the separate base. Traditional tubes required machining and assembling a separate Bakelite base, inserting pins, soldering connections. This was labor-intensive and added size and weight. Could the glass envelope itself serve as the base? Challenge 2. Develop all-glass construction. If pins could be sealed directly through the glass bottom, the separate base became unnecessary. But this required developing glass-to-metal seals that could withstand thermal stress and maintain vacuum integrity. Challenge 3. Miniaturize electrodes. Smaller tubes required smaller internal elements, but smaller elements meant tighter manufacturing tolerances. Precision had to improve dramatically. Challenge 4. Reduce power consumption. Smaller cathodes could operate at lower heater power, but they also emitted fewer electrons. The entire tube design had to be optimized for efficiency. Challenge 5. Maintain reliability. Military applications demanded tubes that could survive shock, vibration, temperature extremes, and humidity. Miniaturization couldn't compromise ruggedness. The RCA team began serious development work in 1937-1938. They weren't starting from zero. Experimental small tubes had existed for years, including RCA's own Acorn tubes introduced in 1935 for high-frequency applications. But Acorn tubes were expensive specialty items, not suitable for mass production, consumer, or military use. What RCA developed was the miniature tube with all-glass construction and integrated base, officially the B7G 7-pin style. The key innovation was the button stem seal. Instead of pinching glass around wires, RCA engineers developed a prefabricated glass disc, the button, with metal wires already sealed through it. This button was manufactured separately under controlled conditions, ensuring perfect seals. The button then became the bottom of the tube envelope. The manufacturing process worked like this. 1. The button stem was manufactured with 7 stiff tungsten wires sealed through the glass in a circular pattern, one position left empty for keying. 2. The electrode assembly, cathode, grids, plate, was built on these wires with precise spacing. 3. The glass envelope, a simple tube, was sealed to the button stem. 4. Air was evacuated through a small exhaust tube in the top of the envelope. 5. The exhaust tube was sealed off, tipped off. 6. The finished tube had pins protruding directly from the glass bottom, no separate base required. This design was revolutionary in its simplicity. The button stem could be mass-produced with high-quality control. The all-glass construction was inherently strong and resistant to moisture. The integrated pin design eliminated assembly steps. More importantly, the design scaled beautifully. RCA could make miniature tubes using similar production techniques to standard tubes, just with smaller dimensions and tighter tolerances. The first RCA miniature tubes, announced in 1939, included a 1R5 pentagrid converter, mixer oscillator, 1I4 IF amplifier, 1S5 detector AVC audio amplifier, 1S4 audio output. These 4 tubes comprised a complete superheterodyne receiver. Each tube measured approximately 2.2 inches tall and 0.75 inches in diameter, roughly 1/4 the volume of a standard tube. Weight was about 8 grams each versus 35 grams for octal tubes. Power consumption, 0.05 amperes at 1.4 volts for the heater. That's 0.07 watts, about 3.5% of a standard tube's heater power. This dramatic reduction meant battery life increased from hours to dozens of hours. RCA demonstrated prototype miniature tubes at the 1939 New York World's Fair, but commercial introduction waited until June 1940 with the RCA BP-10 personal portable radio. The BP-10 was remarkable for its time: 9 inches long, 3.75 inches wide, 3 inches deep, weighing just 3.5 pounds with batteries. It used the 4 miniature tubes mentioned above, plus compact batteries RCA developed specifically for this application. The BP-10 was a true pocket radio, large coat pocket or handbag admittedly, but genuinely portable by one person. It performed comparably to table radios and could run for 25 to 40 hours on one set of batteries. Other manufacturers quickly adopted RCA's miniature tubes. Zenith, Motorola, Emerson all introduced pocket radios in 1940-1941. The miniature tube became the standard for consumer portable radios. But consumer applications were just the beginning. The U.S. military was watching closely. When Captain Peterson and his Signal Corps colleagues saw RCA's miniature tubes in 1940, they immediately recognized the potential. Here was a technology that could make genuinely portable military radios possible. Galvin Manufacturing Company, later Motorola, had been working on portable radio designs for the Army. In 1940, led by Chief Engineer Don Mitchell, they developed the SCR-536 handy-talkie, the first truly handheld two-way radio. The SCR-536 used 5 miniature vacuum tubes in a waterproof case. The entire unit measured 12 inches tall, weighed 5 pounds with batteries, and could be operated with one hand. Transmitted power was modest, 360 milliwatts, but range of 1 to 3 miles was adequate for infantry squad communications. By July 1941, the SCR-536 was in mass production. By war's end, over 130,000 units had been manufactured. The SCR-536 saw extensive combat use. North Africa campaigns, 1942 to 1943, Sicily and Italy invasions, 1943 to 1944, Normandy landings, June 1944, first waves carried them, and Pacific Island campaigns, 1943 to 1945. German forces, after capturing SCR-536 units in Sicily, were reportedly deeply impressed. They had nothing comparable. Japanese forces likewise had no equivalent handheld radio. The tactical advantage was significant. For the first time, individual squad leaders could maintain constant voice communication without telephone wire. Artillery observers could call fire missions while moving. Reconnaissance units could report enemy positions in real time. While the SCR-536 used miniature tubes, the larger SCR-300 walkie-talkie backpack radio, developed in parallel 1940 through 1942, used standard tubes initially, but increasingly incorporated miniature types as they became available in suitable varieties. The SCR-300, introduced in 1942, weighed 38 pounds with batteries, but had 5-mile range and multi-channel capability. Nearly 50,000 units were produced during the war. This radio transformed battlefield communications at company and battalion level. Both radios depended fundamentally on miniature tube technology, either directly, SCR-536, or through the development path that miniaturization enabled, SCR-300's compact design philosophy. By 1943 through 1944, miniature tubes were everywhere in military electronics. Portable radios, various SCR models, aircraft radio equipment, tank communication systems, radar receivers, some variants, field telephone equipment, electronic countermeasures equipment. production of miniature tubes scaled dramatically. RCA alone was producing millions of miniature tubes annually by 1943. Other manufacturers, Sylvania, Raytheon, Tunxil, produced them under license or developed their own compatible designs. The wartime standardization around 7-pen B7G and later 9-pen B9A Novel miniature tubes created an industry standard that persisted into the 1960s. Even after transistors began replacing tubes in the 1950s, miniature tubes remained common in certain applications: guitar amplifiers, hi-fi equipment, specialized military electronics, well into the 1970s. The miniature tube represented more than just size reduction. It embodied several important engineering principles that influenced subsequent electronics development. Integration. By eliminating the separate base and integrating pins directly into the glass envelope, RCA demonstrated the value of reducing part count and assembly complexity. Standardization. The B7G and B9A pin configurations became industry standards, allowing interchangeability between manufacturers. This standardization facilitated mass production and logistics. Power efficiency. The dramatic reduction in heater power consumption, 0.07 watts versus 2 watts, showed that efficiency improvements could enable entirely new applications. Manufacturing innovation. The button stem technique, developed for miniature tubes, influenced later semiconductor packaging. The concept of prefabricating a reliable seal structure and building electronics on it presaged integrated circuit packaging. When transistors emerged in the late 1940s and began replacing tubes in the 1950s, many lessons from miniature tube development transferred directly. Transistor manufacturing used similar principles: standardized packages, integrated connections, emphasis on low power consumption. The engineers who developed miniature tubes, many of their names lost to history, solved a critical problem under time pressure. War was approaching. RCA's work began in 1937-1938, well before Pearl Harbor. The military need was urgent and clear. These engineers weren't working on glamorous technology. Miniaturizing vacuum tubes wasn't as exciting as developing radar or jet engines, but their work had comparable strategic impact. A soldier carrying an SCR-536 in Normandy, calling for support while under fire, probably never thought about the vacuum tubes inside his radio. He just knew it worked. That's the mark of good engineering: invisibility. The same principle applies to thousands of other applications: the pilots flying P-38s with miniature tube radio equipment, the tank crews using compact communication systems, the radar operators whose receivers used miniature tubes for critical stages. All of them benefited from technology they never saw and engineering they never considered. That's how wars are won, not just by dramatic weapons, but by thousands of small improvements in reliability, efficiency, and usability. If you've ever seen a vintage vacuum tube, perhaps in an old radio or guitar amplifier, you might have noticed two distinct types: large tubes with separate Bakelite bases and thick pins, small tubes with glass bottoms and thin pins protruding directly through the glass. The small ones are miniature tubes, descendants of RCA's 1939 innovation. That innovation happened because America in 1939 had no suitable tubes for portable military radios. RCA's solution, all-glass construction with button stem seals, worked so well it became the industry standard for 20-plus years and influenced semiconductor packaging development that followed. The next time you hear about battlefield communications in World War II or see a walkie-talkie in a war movie, remember the engineers who made it possible by shrinking vacuum tubes to 1/4 their previous size. America had no miniature tubes in 1939, so RCA built them just in time for war, and they worked so well that the technology persisted decades beyond the war's end. That's knowledge you now have.